The train in this photo is a maglev train. The word maglev stands for magnetic levitation. Magnets push the train upward so it levitates above the track without actually touching it. Because of the magnets, the trains can go very fast. It can fly over the tracks at the speed up to 480 km per hour. Let's find out what are magnets and how do they exert such force.
A magnet is an object that attracts iron, cobalt, nickel, etc. I have 4 different magnets for you. This is a bar magnet. This one is a U-shaped magnet. It is a ring magnet and it is a cylindrical magnet, also called neodymium magnet. So magnets are of various shapes and of different sizes. But all of them have 2 poles, North Pole and South Pole. As you can see here in this magnet, the impression on this side is N and on the other side is S. This is the North Pole of the magnet and this one is the South Pole of the magnet. Similarly, a horseshoe shaped magnet, ring magnet and other magnets also have 2 poles. Poles are the regions where magnet is strongest. These are the 2 points where the magnetic strength of this magnet is maximum and center is the point where the strength is minimum. Let me show you this with the help of one demonstration. These are some iron filings which I have kept on this piece of paper, on this sheet, and now see, as soon as I have kept the magnet over the iron filings, how these iron filings got collected near the ends. The maximum of the iron filings are near the ends, that means at the poles where the field is strongest. And at the center, the number of filings is very less. Why? Because at the center, the magnet has minimum strength. Similarly, in case of a U-shaped magnet also, concentration of these iron filings is maximum at the poles and almost nothing over here, and few iron filings got collected on the arms of this U-shaped magnet. So this demonstration clearly shows you one very important property of all the magnets, that the magnetic strength is maximum at the poles and minimum at the center. There is a bar magnet over here and there is a nut made up of iron. When I place this iron nut at a certain distance from this magnet, nothing happens. But as soon as I bring this magnet close, the nut gets attached or attracted to the magnet on its own. That means this attraction is not happening right now, but it happens over a distance. Okay? This shows very important property of a magnet. The force that a magnet exerts on certain materials, including other magnets. If I bring one more magnet near this one, then the same thing would happen. They will attract each other. So the force with which the magnet attracts other materials as well as other magnets is known as magnetic force. And this force is exerted over a distance and includes both force of attraction and force of repulsion. That means here I have one north pole, I have the north pole of the magnet and this is the south pole of the magnet. So as soon as I'll bring them closer enough, they will get attracted towards each other. But if now this is the north pole, if I bring this north pole of the magnet close to it, you can see it is being repelled. by the north pole of the other magnet. That means like poles repel each other and unlike poles attract each other. Same thing you can observe with the south pole. This is the south pole of the magnet. This is the south pole of the second magnet. And see clearly what happens. It is repelled. They are not getting attracted to each other, but the force of repulsion is acting now between these two magnets. So this is a very important property that I have shown you just now. Now I have placed one south pole and north pole of the magnets in front of each other and sprinkle some iron filings around it, right? I hope you are getting an idea of what is happening here. Please see that these lines are arranging themselves in a particular way. I hope this has given you an idea that what happens when opposite poles face each other, what happens to the magnetic field lines when opposite poles face each other. Now there are these two south poles of these two magnets are facing each other. I'll tap this board gently to see how these magnetic field lines are arranging themselves. Remember children, like poles repel each other. Please observe that these field lines are going outwards, both the sides. I have these pins with me. These are made up of metals. Now these pins are not attracted towards each other at all, because even if they are magnetic substances, but they are not magnets. I have one bar magnet now with me, and if I bring this first pin closer to the magnet, it gets attracted towards it. But if I bring the second magnet closer to the first pin, see, it also gets attracted to the pin. Similar thing happens with the third pin. And this is how the three pins are joined or attracted to each other because of the presence of this magnet. So you have found that these pins are attracted to the first pin because the first pin is magnetized in the magnetic field produced by the magnet. This phenomenon is known as magnetic induction. It is temporary in nature. On removing the magnet, they have again lost their magnetic properties. That means now they are not behaving as a magnet. Their magnetic properties, or they were behaving as a magnet only in the presence of the external magnetic field. As soon as the first pin loses its magnetism, the rest of the pins fall down.
Let us now recapitulate quickly the properties of the magnets. Magnets show attractive properties to all the other magnets and magnetic materials. The second property of a magnet is that if you freely suspend a magnet, it will always rest in north-south direction. This is because they are all lined up along the Earth's north and south axis, and that is why the poles of the magnet are also called north-south. The Earth's geographic north pole attracts the north pole of the magnet, and therefore this pole is actually Earth's magnetic south pole as depicted in the diagram. Similarly, the geographic south pole of the Earth attracts the magnetic north pole. That means the north pole of a magnet. and therefore the geographic South Pole is actually the Earth's magnetic North Pole. This particular property of a magnet of aligning itself along the north-south direction when it is freely suspended is known as directive property. The third property, when two magnets are brought close to each other, their magnetic field interact. You can see how they interact here. The lines of force from north to south pole attract each other as shown over here. The lines of force around the north and south pole join together. But when two north poles are brought in front of each other, then they repel, and the lines of force around two north pole push apart. This is another property of a magnet which is known as magnetic induction. The process in which a piece of magnetic material acquires the magnetic properties temporarily in the presence of another magnet near it is known as magnetic induction or induced magnetism. In the figure, you can see that this magnet is able to hold pins, and these pins themselves are acting as a magnet which are able to hold other pins also. So these are some of the properties of magnet.
I have brought this magnet closer to the needle, and please observe how it is deflecting. See, on changing the poles of the magnet, it is showing deflection. And if I change the position of this magnet around this compass needle, then also it is deflecting. So this compass needle basically will tell us the direction of the magnetic field lines. So I'll show you with the help of this demonstration what are magnetic field lines. So for this I need a white sheet of paper, iron filings, a magnet and a compass needle. I will spread or sprinkle the iron filings evenly on this sheet of paper, and I will place then the bar magnet in the middle of the sheet, and then you can see what happens. So I have spread these iron filings on this sheet. Now I'll place the magnet at the center, and on tapping this board gently, you will see that after some time these iron filings have arranged themselves in a particular pattern. Iron filings have rearranged themselves in the form of curves, and these lines that you can see, these fine lines that you can see here, are known as magnetic lines of force. These magnetic field lines that you can see here make up the magnetic field of the magnet. The concentration of iron filings near the poles is maximum, indicates these are the areas which exert strongest force. Now if I place compass needle in this position, in this area of the magnet, then you can see that how the magnetic field affects the compasses placed above the magnet. Kindly observe their direction as well. Now I'll place the second needle here. At every point the direction of this needle is different, and the shape is that of a curve. So that means these magnetic field lines are curved actually, and these are continuous curves, right? So this is another demonstration explaining you and giving you the concept of magnetic field and magnetic field lines. The same process I have repeated with the U-shaped magnet, and very fine lines here also you can see, and these lines are nothing but the lines of magnetic field lines, which actually make up the magnetic field of this U-shaped magnet. But I hope you have got this point understood, that every magnet has its magnetic field and the magnetic field is defined by the magnetic field lines. In this demonstration, I will show you the plotting of magnetic field lines or magnetic lines of force around a bar magnet. For this, I have taken a white sheet of paper and a magnet along with a compass needle. I will place the magnet at the center of the sheet. After drawing its boundaries, I'll write the north and the south pole. So if this is north pole and this is the south pole, so I'll place the magnet in this way only, right above the boundaries. Now I will place this compass needle close to the north pole of this magnet and will mark pencil dot exactly at the end of the needle. Place in such a way that one end of the needle, that means the other end of the needle, is exactly above the point which I have marked just now, and then I will follow the direction shown by this needle. I'll continue this process. I'll keep marking the needle, the end of the needle, and I will follow the path accordingly. And see, it has now come here. The needle shows the direction here, right? I will repeat this process for the other end of the magnet. So I will keep the magnetic needle in the north pole on this side of the magnet and repeat the same process. So I'll follow the direction shown by the needle and I will mark these points. Yes. And finally, I will join these dots which I have obtained on both the sides of the magnet. You can very well see here now that I have joined all the points and I have got a continuous curve. So in this way, the magnetic lines of force can be traced. I will now repeat this process from the north pole of the magnet, starting from a different point, and trace another magnetic line of force. So if you observe these two magnetic field lines, You will find that first of all they are curves which are continuous in nature, and also these are not intersecting each other. We can draw as many lines we want to draw. But the concept that we need to understand is that these lines of forces first of all show us the direction of magnetic field lines. They are closed and continuous curves. They do not intersect each other. Direction of the magnetic field line is determined by drawing tangent at a particular point. Tangent means it is a point on the curved path of the magnetic field line which shows you the direction. It is a straight line. So this is a way of plotting the magnetic field lines around a bar magnet.
Let us now understand the cause of magnetism. Every substance is made up of tiny units called atoms, and each atom has electron, which is a carrier of negative charge. These electrons spin like tops, and the electrons circle the nucleus of an atom also. So this movement makes each electron to act like a small magnet, and hence we can say that every atom behaves like a magnet also. In most of the substances, equal number of electrons spin in opposite direction, which cancels out their magnetism. This is why cloth, a piece of paper, wood, or plastic are all non-magnetic substances. But the substances like iron, cobalt, nickel, in all of these substances, most of the electrons spin in the same direction, which makes the atoms of these substances very strongly magnetized. So this is the major cause of magnetism. This is the figure of a substance which is not magnetized, or it is a non-magnetic substance. So if you look at these arrows, what do they depict? They tell us the direction of spin of the electrons, which is random, and therefore it is unmagnetized. On the other hand, this substance which is said to be magnetized, here you will observe most of the electrons are oriented in one particular direction. I mean to say the atoms or the electrons line up in a definite way to create small aligned regions called magnetic domain. So these regions are known as this region is known as magnetic domain, where you will find most of the electrons or atoms aligned in a particular direction. In these domains, the fields from all the individual atoms, that means I'm talking about the magnetic field, from all the individual atoms add up to produce a significant overall magnetic field. And hence, some substances are non-magnetic while some substances are magnetic. Let us understand more about magnetism with the help of this simulation. Now, on clicking the See Inside magnet, you will observe that the domain inside this magnet are all aligned or pointing in the same direction, which gives this material its magnetic ability. The red end of these domains depict North Pole and the white end depict South Pole. So basically the direction of the domain is from south pole of the magnet to the north pole of the magnet inside the magnet. Okay. Now if I click on this show field, then you can now see how the domain's arrangement within this magnet is impacting the area around the magnet. Now look at the area around the magnet. Outside the magnet, the direction of the field is from north to south. All the north end of the domains are pointing towards south. It is going from north to south outside the magnet. But inside the magnet, the direction is from south to north. You can see the actual magnetic field as they are pointing from north to south, and when I move this bar magnet, it impacts the area around it. I hope you have observed the changes very carefully. Now, if I click on this show compass, then on moving this bar magnet near to the compass, you will find that this bar magnet is able to influence the movement of the compass, because this compass is a tiny magnet, so that the north end of the compass, the north end is the red end, right? So the north end of the compass will be attracted to the south end of the magnet. If I flip the polarity, everything changes. Now the south end of the compass attracts the north end of the or north pole of the magnet. At the same time, if you look at the domain, the direction of the domain inside the magnet, it is also reversed. That means it is from south to north, but pointing in this way. And hence you can observe the changes in the magnetic field outside the magnet, the direction of the magnetic field outside the magnet.